in my last class we discussed the power circuit configuration of AC drive. We found that there are two stages of power conversion. One is AC to DC conversion, and again DC to AC conversion. So input is fixed frequency, fixed voltage AC source, and the final output is variable frequency, variable voltage source. Invariably, in most of the general purpose AC drives, the AC to DC conversion is realized using a uncontrolled diode bridge, because it is economical, very rugged. But then the limitations are source current is peaky, so power factor is very poor, also harmonic content is high, and if the AC voltage fluctuates, the output of the bridge also will fluctuate. We know that a voltage source inverter is capable of operating in two quadrants. Current can reverse. It is expected that power will flow from DC to AC side. So when does there is a reverse power flow from AC to DC, or when this load will supply back the power to the DC link? In other words, this induction motor now operates as an induction generator. When does this happen? We know that induction motor always runs at a speed which is slightly less than the synchronous speed. But then to operate as an inverter, to operate the induction motor as an generator, the rotor speed should be higher than the stator frequency or the synchronous speed. The rotor speed should be higher than the synchronous speed. Slip should be negative. Okay. How can you implement this, or how do you operate the induction motor as an induction generator? What is being done is, stator frequency is instantaneously reduced. So the moment stator frequency is reduced, the speed of the rotating magnetic field produced by the stator also reduces. In other words, synchronous speed comes down, or it falls with the stator frequency. Rotor speed cannot change instantaneously. Rotor speed cannot change instantaneously because of it has its own inertia. So therefore, the rotor speed now is higher than the synchronous speed. So slip becomes negative. Induction motor now works as an induction generator and feeds back the power back to the DC link. Okay. Now in the last class we had connected a resistor and a switch in the DC link. We monitored the DC link voltage. As soon as it increases about a certain level, we closed the switch and dissipated that energy. So in high power drives, it is desirable that this regenerated energy should be fed back to the AC source. So that is the reason the input stage should have bidirectional power flow capability. It should be able to supply as well as receive. Second is, it should be able to maintain a constant DC link voltage irrespective of the input AC fluctuation. And third one is power factor should be unity. So these are the desirable features of a high power AC to DC conversion stage. Okay. So here are some of the results that we have taken in the laboratory. Okay. This is a line to line current drawn by the induction motor at 15 hertz, approximately 15 hertz. See, without using an inverter, it would not have been possible for us to run the machine at 15 hertz. The frequency of this current waveform drawn by the induction motor is of the order of 15 hertz. Okay? And this is a line to line voltage waveform. See, it has a large number of pulses. It has a large number of small pulses. Okay. Current waveform is approximately a sinusoid. Okay. This is at 15 hertz. Okay. See, this is at 40 hertz again. See, current waveform is sinusoid, has a very high frequency ripple. In other words, a small current varies over a very small band. Of course, this current is not controlled within a hysteresis band. Okay. Though we are applying high frequency pulses, okay, current is still sinusoid. Okay. See, I extended this waveform. See, it looks like this. See the wave pulses here, large number of pulses. Transition from 0 to the DC link, the rated value is almost instantaneous. Almost instantaneous. In other words, dV by dt is very high. Plus dV by dt as well as minus dV by dt is high. Okay. See the current waveform is almost a sinusoid. Almost a sinusoid. Now I have a question. We are feeding now a stepped waveform. Current is still a sinusoid. See, machine is designed for a sinusoidal excitation. We are supposed to connect it to a three-phase sinusoidal voltage source, and it draws a sinusoidal current. Now, inverter fed machine, line to line voltage waveform has a large number of pulses. dV by dt, positive as well as negative dV by dt is very high, whereas input, if it is fed from a AC source which is sinusoidal, there is voltage changes uniformly. Okay. In other words, there are no transients there. In both the cases, current is sinusoid. How can this happen? So looks like for the motor, it doesn't matter whether it is being fed from a sinusoidal source or this sort of a waveform wherein there are large number of pulses and the variation from 0 to the rated voltage is almost instantaneous. In both the cases, we find that current is sinusoidal. What is the reason? Or how can this happen? One conclusion that I can draw is that if I take the Fourier series of this waveform, it should have a fundamental component, okay, whose frequency is same as the frequency of this sine wave. See, I will repeat, it should have a fundamental component, okay, whose frequency is same as the frequency of the sinusoid, and the frequency of other components should be very high. Okay. Only then I can have a sinusoidal current. Since the frequency of the other component is very high, they get filtered by the stator inductance, leakage inductance. Okay. So therefore, it is not necessary that you should feed a sinusoidal voltage to an induction machine. You can feed any waveform, but then it should have a fundamental component, and the next immediate component, its frequency should be very high. If you ensure that, you will have a sinusoidal current drawn by the machine. Okay. See, sinusoidal current, but then a large number of pulses, the variation from, see, it is clear here, variation from 0 to plus VDC and plus VDC to 0 is almost instantaneous, but then current is still a sinusoid. Okay. So that is about a voltage source inverter. So what are the features? Input is a stiff DC source. In the beginning of inverter classes, I told that you can also have a stiff current source. Okay. So that sort of an inverter is known as a current source inverter, CSI, current source inverter. In order to maintain a constant voltage in a VSI, we had used a large capacitor. Okay. Now we need to have a constant current, therefore we have to use a large inductor in series with the inverter, so that almost a constant and ripple free current is maintained in the DC link. Okay. See the power circuit configuration here. I have just shown 6 switches. Okay. The features of these switches we will see sometime later. A large inductor which maintains essentially a constant current here. Okay. And a variable voltage source, VDC. Okay. So IDC can be varied by varying this voltage. How do I get this VDC? A variable voltage, variable DC voltage, by using controlled rectification. Remember, now I need to have a controlled rectification. In a VSI, current can change instantaneously, current can reverse. It is a 2-quadrant operation, current can reverse, voltage will not reverse, voltage cannot reverse rather in VSI. Just the opposite is true in the CSI. Since we have used a large inductor in the DC link, current cannot reverse there, but then voltage reverses. See here, VI can reverse, VI will reverse polarities. If the polarities of VI reverses, we need to have the switches which are capable of blocking the reverse voltage. Remember, I will repeat, the switches here should be capable of blocking a negative voltage. the devices which we use in a VSI cannot be used here. We had connected a freewheeling diode across the controllable switch. So the moment you connect a freewheeling diode across a controllable switch, it cannot block a negative voltage. So this S1 to S6, either they should be SCRs or G2Os which are capable of blocking the reverse voltage. Now if you want to use IGBT or BJT there, you need to connect a diode in series with the switch, like in this fashion. See here. Okay. Now the switch can block the negative voltage. It can pass the current, unidirectional current. Now diode can block the negative voltage. Okay. So you can use these switches in a CSI. I told that SCRs can be used. If SCRs are used and the load power factor is lagging, we need to use additional capacitor and diodes to turn off the SCRs. I told you in a VSI we had used L and C, separate L and C we had used. So in a CSI, if the load power factor is lagging and the devices are SCRs, you need to forcibly turn them off. So generally capacitors and diodes are used. Okay. And if the power factor is leading, okay, only just 6 thyristors are sufficient. If the power factor is leading, I said this sort of a commutation is known as load commutation. Current becomes 0 first and then voltage becomes 0. So thyristors turn off of their own because current has become 0 and it has reversed. Something known as a load commutation. Okay. So in a load commutated inverter fed drive, there are only 6 thyristors, only just 6 thyristors in the DC. So please recall, maybe while doing the inverters initial portion, I said load commutated inverter fed synchronous motor drive. A load commutated inverter fed synchronous motor drive is nothing but a current source inverter with 6 SCRs, okay, feeding a synchronous machine or synchronous motor, wherein the power factor is leading. Okay, it's very attractive, quite attractive. Okay. Now, what is the difference between a VSI operation and a CSI operation? In a VSI, at any given time, 3 devices are operating. Okay. One switch in each leg is operating. Okay. So you may have a condition wherein all upper 3 switches are on or all lower 3 switches are on. The freewheeling through the positive DC bus or freewheeling through the negative DC bus. There is no problem at all, even if the load is inductive. Okay. It is not necessary that one of the switches in upper half or lower half should be on. It is not an essential condition at all, because there are freewheeling diodes across the switches, so they provide a path for the continuity of current, load current. Okay. And we had used pulse width modulation to control the output voltage of a VSI. We had used PWM to control the output voltage of a VSI, and depending upon the power level, the switching frequency also varies, and you could have of the order of say 10 kilohertz or so. Okay. So if someone says the switching frequency of a VSI is 10 kilohertz, it's fine, it's possible. How about in a CSI? At any given time, only two devices are on, or only two phases are conducting, one in the upper half, one in the lower half. Because in the DC link there is a large inductor. You cannot break an inductive circuit. So at any given time, DC link through the inverter circuit should be completed. Remember, see in this current you cannot break it. You have to provide a path. You have to provide a path by at least one switch in the upper, one switch in the lower should be on. So at any given time, one switch in the upper half and one switch in the lower half, they are on. Okay. In other words, one phase is open. One phase is open. See, this sort of operation we had seen in three-phase AC to DC conversion. Almost the same thing. At any given time, one in the upper, one in the lower device is conducting. Three-phase AC to DC converter. Okay. Because same principle, there also we had a load which is equivalent to a current source type. We had connected assume that this I am connecting to a three-phase AC source. Okay. We had connected a DC link inductor to smoothen the filter out the current, and this I can represent it, or this can be equivalent to the back EMF of DC machine. Okay. Of course, the direction of current of these devices should be in the opposite. Okay. So almost the same operation we have here. At any given time, only two devices are conducting. One phase is open. What about the voltage waveform across the load? Current is independent. Whatever the current that is flowing in the DC link will flow through the load. See, only one switch is open and one switch is open in the both halves. Whatever the current that is flowing in the DC link will flow through the load and back. Okay. Now, depending upon the load, waveform changes. In other words, terminal voltage waveform is determined by the response of the load to the applied current. I will explain to you sometime later. I will show you some of the waveforms. I will repeat, the terminal voltage waveform across of the load is determined by the response of the load, or depends on what sort of a load it is feeding. Okay. And now take for example a three-phase current source inverter. Okay. Again, I am assuming S1 to S6 as switches. Okay. Those so-called self-commutating switches, maybe GTVers. Yes, because if you are using thyristors and if the power factor is lagging, you have to use separate CN diodes. Okay. So I am not going to discuss that aspect, so-called the commutation aspect. Okay. I am taking these 6 switches which are capable of commutating or capable of turning off using gate, or it is possible to turn these devices off using the gate signal. I said any two devices are on and each device conducts for 120 degrees. Same thing, whatever that happened in three-phase AC to DC conversion, each device conducts for 120 degrees, and for 60 degrees one phase is open. See here, IA. In other words, S1 is conducting for 2 pi by 3 radians, 120 degrees. Whatever the current that is flowing in the DC link flows out of the terminal A. From 2 pi by 3 to pi, S1 is also off, S4 is also off. Okay. At pi again, S4 is turned on. Okay. In the B phase, okay, when S1 turns off, S3 should be turned on, okay, because this path should be completed. ID there has to be a path for ID. S1 turned off, S3 turned on, and it remained on for another 120 degrees. So if S1 has S3 turns on here, definitely that phase is off for 60 degrees. Okay, and here S6 is on. Okay. See, at this point S3 or S6 turned off. At this point S6 turned off. In the upper off, S1 is on. So one device has to turn on in the lower off. Okay. S4 cannot, because S4 turns on at pi. So at this point S2 turned on. So if you see at any given time, say from 0 to pi by 3, 6 and 1, 6 and 1. From pi by 3 to 2 pi by 3, 1 and here 2. And from 2 pi by 3 to pi, this is 3 and this is 2, and so on, so on. Almost the same current waveform we had in three-phase AC to DC conversion. So we had assumed that DC link current is constant and ripple free. So phase current or line current that is flowing out is also constant and ripple free. What is the harmonic spectrum? See, we had a line to line voltage waveform, okay, VSI, almost the same. For 2 pi by 3 it is VDC, from 2 pi by 3 to pi it is 0, and again from pi to for another 120 degrees it is minus VDC. Okay, line to line voltage waveform in a 6-step inverter, wherein each device conducts for 180 degrees. We had something like this. What is the harmonic spectrum, or what is the Fourier series that we wrote? It is here. Okay. Harmonic spectrum is 6n plus or minus 1. Fundamental component 5th and 7th. Again 11 and 13, so on. So peak of the fundamental is the fundamental component. Okay. ID sin omega t. the question that is asked, I said current when T1 or S1 is turned off, current becomes instantaneously 0 in that phase, okay, and entire DC link current starts flowing through S3. See here, S1 turned off instantaneously and S3 turned on instantaneously. S1 turned off, S3 turned on. So what is di by dt here? And what is di by dt here? Di by dt is infinity, rate of change of current. So if there is an inductor in the load, can you have this sort of a waveform? See, for 2 pi by 3 to pi, there is no current that is flowing in that phase. No current is flowing in that phase. Okay. Now, see, there is, if suppose there is an inductive load connected here, this current, a constant current was flowing. At this point, S1 is opened. S4 is open and it will be closed after 60 degrees. Okay. So what happens? What happens? Or if there is an inductive load, what sort of a voltage waveform will it be there? Or the question is, can you realize this sort of a current waveform if there is an inductor? If there is an inductor. Answer is no. Answer is no, because it will create a large voltage spike. Large voltage spike. So in other words, changeover from 1 to 3 should be slow to limit the di by dt. In other words, see here, this current should gradually fall, and this current should be gradually rise, so that you should be able to contain, or you should be able to limit the di by dt. Okay, because if you have this sort of a waveform, di by dt is going to be infinity. Okay, that will create a large voltage spike. What did it happen in voltage source inverter? In fact, we had used very fast devices. We wanted almost instantaneous changeover from one device to another device. Load may be inductive. Why here we need to have a gradual fall and gradual rise? Reason is very simple. There are the freewheeling diodes take care of this inductive energy. There are no freewheeling diodes here. There are no freewheeling diodes. So these are the differences. Okay. You cannot have this fast rise and this fast fall. Okay, its changeover should be slow to limit the di by dt. Okay. See here, the inductive load, in a VSI, you could have inductive load. I am not saying that we are changing the current in an inductor instantaneously by opening the switch. In fact, we wanted a very fast switches here, very fast switches. The moment I open the switch, I don't need to close this, current will start flowing through this diode. That maintains the continuity in a VSI. Okay. So LDI/dt spike depends on the leakage inductance. I said in a CSI, terminal voltage waveform is governed by the load. Whatever that current that is flowing in the DC link will continue to flow through the load. Now, load voltage waveform depends on the type of load. I'll just explain here. See, assume that you have a back EMF and inductance in series. Resistance I am neglecting. Something similar to an induction machine, maybe. Something similar to an induction machine. Back EMFs, inductance. I am assuming E1, E2, E3 to be sinusoidal. Okay. Now, see, this is the one of the phase current waveforms or line current waveforms, IA. Assume that it is IA. It was negative, became 0. For 60 degrees, it remained 0, and again a positive current. So there is a positive LdI by dt, again there is a positive LdI by dt. So what is the voltage here? E1 plus, so there is a LdI by dt here and LdI by dt here. There is no LdI by dt here, it is 0. So there is going to be a spike these 2 points. Okay. So this way, how do I reduce this spike? One is to have a gradual transfer. Of course, if it is slow, it affects your power transfer. So another way to decrease the magnitude of the voltage spike is to have a low leakage. So if the machine is being fed by a current source inverter, it is desirable to have low leakage, or machine with low leakage is desirable. Just the opposite is true in a VSI. Why? See, what is the expression for the harmonic current? See, here is the expression. The magnitude of harmonic current of a given frequency is equal to the magnitude of that harmonic, magnitude of that particular harmonic, divided by the impedance offered to that harmonic. I am neglecting the resistance now. Okay. So IH current decreases as L1 increases. See here. So IH decreases as L1 increases for a given harmonic voltage. Whereas, so therefore, higher leakage is desirable if the machine is being fed from a voltage source inverter, and in case if it is being fed from a current source inverter, low leakage machine is desirable. Is that okay? See, this current source inverter fed induction motor generally used for high power application. CSI inverter is invariably used for high power application. Okay, because one of the advantages is circuit is very rugged. So in case S1 and S4 they conduct at the same time, nothing is going to happen because we have a large inductor in the DC link. It has an inherent short circuit protection. Okay. Whereas in a voltage source inverter, you just cannot afford to have a short circuit in the DC link, or you cannot allow S1 and S4 to conduct at the same time. So that's the reason we use really fast devices there. Here, slow devices or slow devices can be used. Another advantage of current source inverter is that all 4-quadrant operation is possible, or in other words, it is easier to have 4-quadrant operation in a CSI fed drive. Okay. How is that possible? See here, a large inductor, AC to DC conversion. I said we need to have a variable voltage here, regulated variable voltage here, which you can realize it using control rectification, 3-legged inverter feeding a machine. So at any given time, operation is in the first quadrant. T is also in this direction, omega with plus minus plus minus. Okay. Now input voltage is positive, current is also positive. Source is supplying power to the inverter and to the load. I had told you that this voltage changes, or polarities of this voltage will change in a CSI. Now we want to go to second quadrant or fourth, depends on which one you have taken, T along x axis or y axis, it does not matter. So what do I need to do? I have to interchange the polarities here by increasing alpha above 90. I can still, of course, current direction is the same. You cannot reverse the direction of current. Same thing, just the opposite, dual is true in now VSI. Voltage polarities cannot be reversed. Current will still flow in this direction. See the polarities of VDC and V in voltage inverter. Okay. Torque and omega. Operation has changed, has gone to some second, has gone to another quadrant. Okay. So maybe a regenerative braking. Speed will fall. Okay. So as the speed falls or near the zero speed, okay, you want the motor to rotate in the reverse direction, you interchange the sequence of the SCR or device triggering. When you interchange the sequence of triggering pattern, indirectly you are interchanging the phase sequence. Okay. So if you change the phase sequence, machine will try to operate in the reverse direction. So now you are in the third quadrant, the so-called the reverse motoring. And maybe from there you go to another quadrant, either second or fourth, depends on how you came from first to third. So in other words, regenerative braking or all 4-quadrant operation in a CSI fed drive, it is very simple to implement. We have just a controlled AC to DC rectifier, and here again an inverter. Okay. Whereas in a VSI, we wanted or we used a bidirectional power converter to feed back the power that is received from the load to the source. We use a bidirectional power converter. The device is capable of carrying the current in both directions. Whereas here we are using just 6 thyristor in the AC side. Okay. So these are the advantages of a current source inverter. Of course, it is current source CSI inverter is quite vast. Okay. But then the voltage source inverters are more popular. Popularity wise, VSI is far ahead than a CSI. Okay, because There are large number of low power drives. There is, I have not gone into analysis of a CSI using SCRs, the so-called commutation circuitry. Of course, I have not done even for a voltage source inverter. There also I had assumed the self-commutating devices. Even in a voltage source inverter, we had used self-commutating devices. But then I cannot use those same devices in a CSI. I need to modify them. But in case if you use SCRs, you need to forcibly commutate them. Okay. So that is about the inverters as a whole. Okay. What did we do in that whole inverter chapter? We start off with the basic building block of bridge inverter. Then we went to full bridge, single phase, 4 devices. From there, 3-phase VSI. We discussed 180-degree conduction, square wave operation. There are harmonic problems. Okay. Then after that, we use various pulse width modulated techniques, PWM techniques, to control the output voltage. And we found that suitably, if you turn the devices on and off, you can eliminate a certain harmonics. Okay. In the conventional inverter wherein only 6 devices are used, there are only 2 levels in the pole voltage waveform, either 0 to plus VDC or minus VDC by 2 to plus VDC by 2, depending upon which point you have taken as a reference. The pole voltage, there are only 2 levels, hence the name 2-level inverter. So I had told you that as the power level increases, switching frequency should come down. Okay. So instead of using pulse width modulation, I said we can have more number of levels in the pole voltage, thereby synthesizing approximately a sine wave. Okay. So this sort of inverters are known as multi-level inverters. The pole voltage has more than 2 levels. I said these are popular in high power applications. From there onwards, we started discussing a current source inverter, CSI fed inverter. Here I may not have gone into detail, but I try to tell you the operation of the inverter. DC link current waveform or DC link current is maintained constant. Load voltage waveform now depends on the type of load. Okay. I told you that transfer from one device to another device should be slow to limit the di by dt, and 4-quadrant operation is easier to implement, and these drives are used or CSI used for high power application. So line current waveform in a CSI is a square wave of 120-degree duration. So there are 6 and plus or minus 1 harmonics. Okay, there is a 5th, 7th, 11th, 13th. What did we do in VSI to eliminate the harmonics? We had used pulse width modulation. So similarly, can we use pulse width modulation to eliminate these current harmonics? Answer is no. In other words, pulse width modulation is not very popular in CSI. Okay. So because first of all, we have used slow devices. I said in order to limit the di by dt spike, the current transfer from one device to another device should be slow. So if I am using pulse width modulation, that means I need to turn off S1 and S3 simultaneously. Okay. The problem may get aggravated. Okay. So PWM is not very popular in CSI fed drives. Okay. Another main difference in a CSI and a VSI is that you need to have closed loop operation in CSI drive. Closed loop in the sense we need to monitor some output quantities, okay, maybe speed we need to monitor, and depending upon the required speed we may have to set some current in the DC link. See, arbitrarily you just cannot have some current in the DC link, because that current is flowing in the machine and it is going to produce some torque. Where does the machine operate now? Where the electromagnetic torque and the load torque intersect each other is the operating point. So you have no idea about the load requirement, and just setting up some current in the DC link, you may have some sort of an unstable operation. So you can set a DC link current based on the load requirement. So in other words, a closed loop operation is the must in a CSI fed drive, which is not required in a voltage source inverter fed induction machine. Okay. So with that we have come to an end of inverter chapters. I just try to give an overview of inverter chapters. It's a vast subject by itself. Okay. For first course in power electronics, this should be sufficient. Okay. If you are interested more, I would encourage you to go back to the library and read. Okay. So therefore, we have covered 3 important chapters in power electronics. What are they? The first one is AC to DC conversion. We call them as rectifiers. Then DC to DC conversion. So depending upon the power level, we said choppers or switch mode power supplies. And the third one is DC to AC converters. Okay. So what about the last one in the power electronics standard? That is, input is AC, output is also AC. Okay. Again, there are 2 different classes. The first one being both frequency as well as magnitude variable. See, I have a converter here, input is AC, output is also AC. There is no conversion from AC to DC and DC to AC. Direct AC to AC conversion. Okay. So first class is input is fixed frequency, fixed voltage AC, output is both voltage as well as frequency variable, direct conversion. And second one is frequency constant, magnitude variable. Okay. The second class of inverters, the equipment which belong to the second group, they are known as phase regulators, okay, or phase controllers, or AC voltage regulators. Okay. We will study this class of controllers in detail. By the way, where are they used? There is a fixed voltage as well as frequency source, and we want frequency constant, voltage, magnitude of voltage variable. Where could this equipment be used? One, a general purpose application is fan regulators. What are we doing there? In order to vary the speed of the fan, by changing the knob of the regulator, what exactly we are doing? We are applying reduced voltage to the machine or to the fan motor. Frequency is being untouched. Frequency remains the same. Okay. So similarly, in a temperature controller, suppose you want to control the temperature or vary the temperature, we are just changing the knob. What exactly we are doing? We are applying the reduced voltage to the load. Okay. Lighting intensity controller. There is a knob. We are turning the knob, we are reducing the intensity of the bulb. What are we doing there? Same thing. Frequency constant, varying the magnitude of voltage that is being applied to the load. Okay. The principle of operation of these circuits we will study in the next class. Thank you.